So we had looked at finding absolute extrema, absolute maximum, and absolute minimum values on a graph or given a function. And I quickly want to kind of review these definitions and theorems, and then we'll move on. So definition, we're going to let f be a function with some domain capital D. Then f has an absolute maximum value on D if the point at a point C, if f of x is less than or equal to f of C for all x in D. Okay, so it's the biggest value anywhere on that interval, or biggest value and equal to maybe another value that has that same y value. An absolute minimum on that D at C is if f of x is bigger than any or greater than or equal to f of C. Okay, so it's the smallest value on the graph. Okay, so we looked at that last week, what it meant to be an absolute max, absolute min. And then we looked at this extreme value theorem. So this extreme value theorem, and they call it theorem 1 in our book for this chapter, it says, and these conditions must hold when we use this. So it says that if f is continuous on a closed interval, so right there, that's really important. It has to be a closed interval that we're looking at. If we're not looking at a closed interval and we're not including those values A or B on that end of the interval, then this theorem does not hold. So if we're on a closed interval, that function has to be continuous on that closed interval. So if there's any jumps in the graphs or any holes, then this theorem doesn't hold. It says then f attains both an absolute maximum value, they call it capital M, and an absolute minimum value, little m, on that closed interval AB. That is, there are numbers x of 1 and x of 2 in that closed interval AB, where if we plug in x of 1 in for our function and got our y value, and that was equal to little m, and let's say we plugged in our x of 2 value, that's where the biggest value occurred at, we plug it in and find our y value, that would give us the capital M value. And it has to follow that little m is less than or equal to f of x, which is less than or equal to capital M for every other x in that closed interval. Okay, so I hope this is helpful just to quickly kind of review through this, and then we'll look at any examples that you want to look over that you were struggling with in the homework. Definition, pretty much we already kind of stated this, but a function f has a local max. Actually, we were talking about absolute before, but a local max value at some value point C within its domain capital D if f of x is less than or equal to f of C for all x contained in D lying in some open interval. That's a mouthful, right? Basically, you might have multiple places where you have maximum values or minimum values, but if we can take this and put a little closed interval around there or interval around there, and it is the biggest value for that interval anywhere in here, then it has to be a max. So same sort of idea for a minimum. A function f has a local minimum. So there's could be more than one value at a point C within its domain D if f of x is greater than or equal to f of C for all x in D lying on some open interval containing C. So in here we have some mins, local mins. So we're going to be looking at this. We're going to be graphing functions, looking at our derivatives, finding where our functions are increasing, decreasing, local max and local mins. We'll get into concavity a little later this week, but putting this all together and being able to graph our functions. This next theorem is how we would find where we would have any local max or local mins. And this is the first derivative theorem for local extrema values, which this says if f has a local max or a local min value at an interior point C of its domain, and if f prime is defined at C, then it must equal to 0. Derivative must equal 0, which again, if we think about the derivative is the rate of change, we knew that when the derivative was 0, we had a horizontal tangent line, and we saw that we had either local max, usually, or local mins there. We're almost there. Last thing, finding your absolute extrema of a continuous function f on a finite closed interval. First thing that you had to do was you had to find your critical points on that interval f. That meant we had to find where f prime of x equals 0. We're going to see later, we also need to look at where f prime of x is undefined. So once you found the derivative, found your critical points, we're going to evaluate f at all critical points and endpoints. So we're going to go back in there on that closed interval. We're going to look at our value on the left-hand side of that closed interval, plug it into our original function, find any values that was equal to 0, plug that into our original function. And the other side, the right-hand side of that closed interval, plug it in. The largest and smallest values are going to be your max and mins, absolute max and absolute mins. Okay, so we had quickly went over that last week. I didn't want to rewrite this all out, but I wanted us to kind of talk about it and then look at some examples. Okay, so we have in front of us some graphs, and it says in these exercises number 1 through 6, determine from the graph whether the function has an absolute extreme value on that closed interval AB, and then explain how your answer is consistent with this theorem 1 that we talked about just a second ago. So recall that theorem 1 basically said, first of all, we have to make sure that our function is continuous. If it's not continuous, then this extreme value theorem is not going to hold, or might not necessarily hold. And it has to be a closed interval on AB. So if we look at number 1, notice that this is a continuous function. And it's a closed interval because of those points. So determine whether the graph has an absolute extreme value. So this would have an absolute max and an absolute min. And if you look at it, the absolute max, the highest value that we get, occurs when x equals b. And then the lowest value occurs, this y value, right? This is smaller than this one. So the lowest value here, this is where our absolute min is. Okay, so the theorem held because it was a closed and continuous function. It's continuous over a closed interval. So same sort of idea happens if you look at number 2. This is closed because these are solid circles on some interval, and it's continuous over this interval where x equals a through x equals b. So an absolute max or an absolute min can either occur at your end points of your interval or on some value in between. So notice here, this is the highest point, highest y value on our graph. And so this is where our absolute max occurs. And then the smallest y value, you're looking at that and you'll see that occurs when x is b. So our absolute min occurs at x equals b. If you look at number 3, this theorem doesn't hold. This is not a closed interval on AB. Those are open. It doesn't include A and it doesn't include B. If you look at this though, so it doesn't have an absolute min. It actually does have an absolute max. And that's when X equals C. So that's not the absolute max itself. The absolute max would be f of C. So what is that Y value? When X is C. Notice here though, this is not differentiable. This is a sharp corner. So when we were taking the first derivative, we would find that X equals C. The derivative, it was it wasn't defined at X equals C. Number 4, same idea. This doesn't have, the conditions don't hold for that mean value theorem because, well, a couple reasons. These are open intervals and this is not a continuous function. It's not continuous at X equals C. And so in here we have no absolute max or min. So I think from there that you guys get the idea. If you look at 5 on the values from A to B, it's not continuous. It is a closed interval, but it's not continuous. So it's not necessarily true that it could have an absolute max or an absolute min. Notice though at X equals C, that's closed there. And we can say that's the highest Y value on the graph. So right here, and this is G of C. This is our absolute max. If we look at this here, the smallest Y value, if you look at it, the smallest Y value we get back is here when X is A. This is closed here, so we're okay. And so we do actually have an absolute min here when X is A. So G of A is an absolute min. Last but not least, number 6, the condition doesn't hold for that extreme value theorem. It's not a closed interval, it's just closed on the right-hand side at B. This is continuous everywhere, well, not at X equals A, but from to B. If I look at this though, this has an absolute, let's see, minimum at X equals C. So that's the smallest value. You look at this 2 here, this is a closed point. And so this actually is a highest value here. So f of A is a max. Absolute max. Okay, so if the condition holds for the extreme value theorem, it must have an absolute max or an absolute min. if the conditions don't hold for the extreme value theorem, then it's not necessarily true that it will have an absolute max or an absolute min, but it is possible. But we can't use that theorem. Okay, so there was a good question about number 4 and why 4 doesn't have an absolute max. It has to do with this closed or this open interval. So on the left, this looks like I'm getting closest to the highest value here when we're approaching x equals a on the left-hand side. The problem is if you give me some value at x equals a on the right-hand side of it, I could give you a value that was even higher up. So let's just say that this was kind of zoomed in here. And so you're like, okay, well, this value here, x equals a, that looks like it's the highest value that's going to hit on this graph here. But I can come in here and say, no, I can find something even closer to x equals a, and that is even higher on the graph than what you gave me. But we can keep playing this game because this is an open circle. So for instance, if this was a was 1, I could say, okay, you gave me 1.1, I'm giving you 1.01, that's even higher. You said, okay, well, I'll give you 1.001. And I said, no, I can give you even a value closer to x equals a or x equals 1. That will give me a higher y value. So that's why it has to be closed interval in order for it to actually, for sure, have an absolute max or an absolute min. So same kind of reasoning here at x equals c. And here we can get closer on the left and the right of x equals c. It's not defined at this value for my y value, but I can get closer and closer and get smaller and smaller values. So for number 4, we don't have an absolute max or an absolute min. Okay, so I noticed that I was on the wrong screen when I was doing that and explaining that, so probably didn't follow along as much, but basically you could see how I was getting closer and closer to A in here and getting a higher and higher Y value, or closer and closer to your C value. We can get lower and lower.